Hello everyone. So we'll wait for a few minutes more and then we'll start the session. Good afternoon. Okay, so I am a research scholar. My name is Simran Kumari, and today we'll be solving some sample questions related to week 1 of control engineering course. Also, if you have some doubt, then we'll discuss about that. Okay. Uh, so Okay, fine. Then let us start. Okay. So this is the first question. Here it says that let us consider system one. So we have one system which is okay. So system one that we have is yt equal to xt plus c, where x is the input, c is bias, and y is the output. And system 2 that we are having is zt equal to xt. So xt is simply the input and zt is the output. I think we have to wait for few more minutes because everyone is joining. So let us wait for few minutes, then we can start. So these are the two systems, and there are four options that is given regarding the system, that we have to identify whether the system is linear or not. Now, regarding the system, if there is some system given to us, whether it is linear or non-linear, this linear system satisfies some property like superposition, which is basically combination of homogeneity and additivity. So if the system satisfies that property, that means that system is linear. Otherwise, we can say that is not linear, it's a non-linear system, or maybe it may be affine system also. So let us see. For the first system, if we take x1 as the input, x1t, and another input, suppose x2t. Now we'll take linear combination of these two. So alpha plus beta x1t. Now this input will be applying to both the system, and we'll see what is the output. So for linear system, what we expect, that the output should be alpha y1t plus beta y2t. Okay. Now for first system, we'll see if we apply this one. So what will be the output? The output will be alpha x1t plus beta x2t plus c. And if we see this one is alpha x1t plus c plus beta x2t plus c. So this one is definitely not equal to this one. Therefore, we'll say that, okay, this is not a linear system. This is not also not a non-linear system. This one is a affine system because of the bias. Okay. The second system that we are having is z equal to xt. So if we apply the input, if we apply alpha x1t plus beta x2t, then output will be simply this one only. And if we say alpha z1t plus beta z2t, this is also equal to alpha x1t plus beta x2t. So we can see these two are equal. Therefore, this system is linear. So we can see the option 2, which is given here, this is the correct one. Any doubt in this question regarding identifying whether a system is linear or not? If you have any doubt, you can ask. Okay, fine. So we'll proceed to next question. This is the second question where it said this is a system y equal to of xt plus x square t minus 1 plus x of t plus a. Now we have to identify regarding linearity of the system, also causality of the system, and whether it's a which type of system, whether it's dynamic or it's a static system. Okay. Now regarding the dynamic system, we know that a system is static if its output depend on the present input. So if this is at time t and the input is also give like the value of input is at time t, then this will say that this is a static system, but here we can see that output at this time depends on input at this time, and then t minus 1 and t plus a, where a is less than 0. So obviously this is not a static system. This one is a dynamic system. Now we are clear with what type of system it is, whether it's dynamic or static. Now coming to linearity and non-linearity. So obviously, if we apply alpha x1t plus beta x2t as input, so see y1t equal to, suppose we apply just x1t. So apply x2t, then y2t equal to 2 of t plus a. Now, if we see what would be the solution, if we say alpha y1t plus beta y2t, this will be summation of these two with scaling factors. This will not be equal to, okay. So this will not be equal to obviously y of y when we give alpha x1t plus beta x2t. Therefore, this is not a linear system and it's a non-linear system. So we have two options, non-linear and dynamical we have found out. And now regarding causality, so what is the, when do we term a system causal? When the output at the time instant t depends on the input at the present time t and the past time. So if we see this output depends on present time t, then t minus 1, one time step like prior, and then t plus a. So where it is given that a is less than 0. So that means this is a delayed version of this one. So therefore, this is a causal system. And we got the answer, which is option D. Any doubt in this one? So if not, then we'll proceed to next question. Okay. This is the third question, which says this is a system yt equal to tx 2t plus 2, where yt and xt are input. Obviously, we are having system, so we'll have some input and output. This is the system. We are having xt as input. This is the output yt, which is equal to. Now it says that whether it's a linear system, time invariant, or causal or not. So we'll first to linearity, we'll apply x1t and x2t with the linear combination. So what will be the output? Suppose we apply x1t, so this will be tx1 2t plus 2. This is the y1. What is the y2? So tx2 2t plus 2. This one. Okay. So now we will be applying alpha x1t plus this one. So this will be alpha t x1 2t plus 1, sorry, 2t plus 2, and then beta t x2 2t plus 2. Now this we can say that if we this t is common, so alpha x1 2t plus 2 plus beta x2 2t plus 2. So that means this is equal to this t into this one. Therefore, we can say this is a linear system. Okay, fine. We have find out that this is linear, and then now we want to see whether it's time invariant or not. So obviously this yt, what is the principle of like time invariance is that if we apply xt, we can say that this depends on time, but since we have to do it mathematically, so xt will give yt, and if we apply xt minus tau, like delayed version of input, this output will also be a delayed version. So if we apply xt minus tau, what will be the output? This will be tx 2t minus tau is 2. And what is t minus tau? This is t minus tau x of 2 t minus tau plus 2. So obviously these two are not equal. Therefore, this is not a time invariant system. This is a time varying system. So we have this option, time variant. And if we see this output as time t, it depends on 2t plus 2. If we keep t out, t plus 1, something like that. So it will depend on a, even if we don't say, then this is a plus. So it says that future value of the xt. Therefore, it's a non-causal system, because for causal system, it should depend on present and past input. So this is correct. Any doubt in this one? Okay, if you see, no, this yt is dependent on tx 2t plus 2, no? So if this is a causal system, this will depend on suppose txt, something like that. So this is dependent on present time only. But we have time delayed version, no? Or time we can say shifted version. So this plus says this shifts the plot of the x. So if this is the plot of x, this is a shifted version. So it depends on future value. Is it clear? Okay. Time variant. Okay. So if you see, the concept of time variant is that if you apply an input and you see the output of system, so this output should be same if we apply the delayed version. Basically, if there is a, this is the input we apply, and this is the output that we get. Okay. Now, if we apply input at some time t equal to t dash, here it was applied at 0. So it is shifted. So this is the input. The output should be same, but since this input has been applied here, so it will be just a shifted version of the earlier output. So that says that xt minus tau equal gives yt minus tau. This one. Now, if we apply xt minus tau, so this will give t x of, since this is the function of x, so like t, x is a function of t. So 2t minus tau plus 2, because the actual function was yt equal to 2x 2t plus 2. Okay. So this is the output yt if we give xt minus tau. And if we have this, you can say it like this also. And if we see yt minus tau, so this will be t minus tau x2t minus tau. So obviously this is not equal. No? I mean, if this is the response, some kind of assume, then this is the not the response, similar response. Suppose this is like this. So the response is varying with time shifting input. This is generally here it is due to time varying system, like because of time, but generally it is due to parameter variation. So if we suppose we take RLC circuit or something, what we assume that RLC values are constant, it doesn't vary with time. But in actual case, there may be some variation with time due to different environmental conditions. So this is kind of assumption which is simple and gives result up to like much accuracy. Is it clear? Okay, fine. And then we'll proceed to next one. Okay, so this is the dynamical system. Now we are, earlier we were dealing with systems and we are finding out what type of system it is, whether it's causal, it's dynamical, it's linear. So now we have come to dynamical linear time invariant system. So we'll be seeing ODEs, V dot or Y dot, something kind of that. So it says, so we are saying dynamical system, that means there will be some energy storing like memory and all, integrators and all. Okay, fine. So the term which represents loss of energy in model equation of, this is quiz control. Cruise control of car whose dynamics is V dot plus D by M, V equal to F by M, where V is the velocity of car. Okay. So if we consider a car and this is moving, like having a force F that is being applied, and suppose this is the displacement. Obviously this has been discussed in the lectures, so we'll just having a quick review so that we can understand what the question, how to solve the question. Okay. And there is a friction because of which there is some energy dissipation. If this is not present, okay. So how will we write the equation? So it's like mx double dot equal to f minus b x dot. That's the damping coefficient. Okay. Now if we say x dot equal to v, we are having because this is a second order system, so we are basically converting it to first order system. So we have assumed that x dot equal to v. Now this will be m v dot equal to f minus vv. So m v dot equal plus vv equal to f. We can see, if we see the equation and we have got this one, So we can do reverse. We can go reverse, no? Now we'll say that okay, x dot equal to v, and then we'll get to this one, and this we can see from this physical system representation that this dynamics is there this dynamics is there because of when we are considering this friction. If we have not considered friction, it will be simply mx double dot equal to F, which we generally see in Newton's law that force is equal to, but obviously that is net force. So net force is F minus bx dot. So we'll having this equation, and then this term will not be there because it will be V dot equal to F by m simply. So this coefficient, this one will be showing the loss of energy. Any doubt in this? Okay. So this is next question, pendulum. Okay, so we have to, in order to get time period of a simple pendulum as half the initial time period, the length of a string should be. Now, time period is basically when we say oscillations and all, then we try to find the time period. So we have, suppose this is a response which is oscillating response with time. This is the theta angle of the, suppose this is a pendulum. So this is the angle of which pendulum makes with the vertical axis. So this is kind of oscillating response. So if we try to find what is the time period of completing one oscillation, suppose going from there to there. Okay, this we have to find, and we have to find out also that what should be the length if this is decreased to half. So if we talk about pendulum, obviously we have this equation, no? That mg is acting in this direction. We have mg sine theta. And suppose this is the length L. So m theta dot equal to minus mg sine theta L. Torque into distance. Sorry, force into distance, so that we get the torque. Now we have theta dot plus, sorry, this one. Yeah, good evening. This will be I theta dot, no? Because we are talking about rotational motion. So this will be the inertia. Sorry. Yes. So mg L sin theta equal to 0. Now this is the equation that we get from the dynamics of pendulum. So this is a non-linear system. Doubt or what? Yes. Manish Kumar Verma, you have raised your hand. Is there in now? Which topic? Can you tell the topic name? Which topic? That I understood, but I have to solve the first week questions, sample questions, and then I can discuss. No, so until unless you tell me which topic you are talking about, how could I know? Okay, so this is a nonlinear system. Now we have to find the time period. So for oscillation around this point, we'll just linearize it around this one so that we can do the analysis because we are comfortable with linear system. Now, if we say that basically we are assuming that this generally we find Jacobian and all, but we'll not go into that deep. We'll just simply say because we have to linearize it around this vertical axis. So we'll just assume that theta is very small. So we'll get theta dot plus mgl theta equal to 0. So this is the equation now we have got. Now this is a linear dynamical system equation. So from here, we can say that theta dot equal to minus mgl theta by j, which is j is ml square. So we'll just have minus g theta by l. And this theta dot, since you have studied transfer function and all, so we can go through that uh, method also, but okay, fine. So if we say that it is s square theta minus g theta by l. Now this is a second order system, and its root are on imaginary axis. So you will understand when will be doing the classes of I think second or third week. So this will give the like this radian per second frequency, which is root g by l. This theta will cancel out. This will be minus omega square, and then minus minus will cancel out. This will be this. Then time period is, I think, omega by 2 pi, no? So 1 by 2 pi or something like that. Okay, omega equal to 2 pi f. So t equal to 2 pi by omega. So this will be 2 pi by omega. So 2 pi root under L by G. This is a time period. Now this time period is half of previous time period, no? Earlier time period. So 2 pi root under L by G is equal to 1 by 2 pi root under L previous by G. So we can say it like this. Now this one is 4L equal to L previous. So L is equal to L previous by 4. So we have got this one, 1 by 4 of initial length. Okay. Any doubt in this? Which from where? From the starting or some point that you didn't? Okay. So for pendulum, if we see the dynamics of this system, this pendulum system, pendulum are basically a string. Okay. So here we have this force mg which is acting. Now this is a causation. This is the input, like we can say to the system, but or we can have the external input which will be the T. Now this T is not present, which is the input given by the controller, or we can say external. This is the acting force. So we have this equation I theta double dot equal to minus mgl sine theta. Okay. So this will be the equation for the pendulum dynamics. Now this equation, this dynamics is nonlinear because of this sine theta term. And we have to find the time period, and we have to say what should be the length, so that time period is half of the initial time period. So for that, to do the analysis, since we are considering pendulum and we are saying that okay, pendulum is accelerating about this vertical axis, so what we assume that this theta is very small, so we can write sine theta as theta, and we get a linear dynamical system, linear time invariant dynamical system. So basically, uh, this is like shortcut step, or one thing we can do is to linearize this dynamics around this angle 0, which is the vertical axis. So from there also we'll get this equation, and if we solve this from, if we see this equation, so we can see if we go through transfer function analysis, or so that will be js square theta plus mgl theta. Now this is a second order system without this damping term, so there is no loss of energy. That's why it was oscillatory, and it has frequency which is root under g by l, because these two terms will cancel and this will give this frequency. Then we can find the time period because we have got the frequency. So this is simply 2 pi by omega. And since we have found out the time period, so equation for basically pendulum, then we can apply this time period equation directly to the thing that question given in the question, that t equal to half t previous, and from there we can get what is the length if the previous length is given. So this is simply previous length by 4. So 1/4 of the previous length. Is this clear? Okay, so you have done this transfer function class. Have you gone through that class? Laplace transform, but after that you will be studying this first order system and second order systems and all. So basically I can say that this is theta dot equal to minus mgl theta by j. Okay, so simply I can say that this theta double dot is a function which is minus alpha theta. So this is one thing that I can say, and from there I can get this mg by l theta. So where is it? So this theta theta will cancel, so theta square. And from there you can get the omega, because this negative, this is a term that is given if you like try to find out this time period thing, then this is a method. But if you go through transfer function thing, then it's like j theta dot plus mgl theta equal to 0. Now if you convert this to transfer function thing, so suppose this is a, there is a torque which is being applied, okay, then only we can write the input output transfer function na? Okay. And if we consider there is no input, so this is just a homogeneous, this is 0 and this is a homogeneous OD. Now, if we find the roots of homogeneous OD, this homogeneous OD, this will give you so we say s square j plus mgl theta equal to 0. So theta will be out, s square j plus mgl equal to 0. So you have to find the root of this, s square j plus mgl equal to 0. Now we have to find time period, and we know that there is no damping in this. So we can just simply replace this s, because this is a complex frequency. No, we can replace this by, this one is sigma plus j omega. We'll simply replace this by j omega, because this term is not present because there is no damping. So this will give j omega square j. This is a small j, okay. MGL, this is messy. Okay, fine. So this will be minus omega square j plus MGL equal to 0. And then we can find omega square. This minus minus will cancel out. MGL by j, j is ml square, so this is simply g by l. This is hell lot of messy. I don't know whether you'll be able to understand. Should I write it again? Okay. 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 Fine. Any other doubt in this question? Okay. So this is next question. And this is a system, this is spring mass damper system, and a force U is being applied. Okay. There is a displacement of car, we can say y1, which is changing this position, and mass of car is m1. K1 and B are spring and damping coefficient. So it is saying what is the correct model of the system in this one. Now, obviously, this is a dynamical system. So how do we write it? There is a force U that is being applied. So this is a force V, U, which is being applied. Here there will be displacement Y1, and because of damping factor, there is a force corresponding to Y1, there is a velocity Y1 dot. So because of this damping, there will be a force which is acting opposite to the motion of this one, which is V, small v, and y1 dot. And then there is a spring which is also there. So this force, since it is being elongated because this is moving in the direction, so it will also have a force which is acting in this direction, which is K1 Y1. Now, if we equate this one, so you will get M1 Y1 double dot, which is acceleration, is U minus B Y1 dot minus K1 Y1. So from there you can get M1 Y1 double dot plus B Y1. Okay, I think I have made some mistake. No. Okay, so K Y1 equal to U. So this is a dot notation, so we'll simply write M d2y by dt square plus B dy by dt plus Ky1 equal to U. This is the equation that we have got, which is this one. Any doubt in this one? Okay. So this is a system and we have a mass M1. It is saying that this is a displacement y1, and if there is displacement, obviously we will have some velocity y1 dot, and correspondingly if we will have some acceleration. This may be zero non-zero, but we are not bothered about this. We are just trying to find out what is the dynamics of the system. Then we have this force which is being applied, which is U. Because of damping, this is a this will what will do, because this mass is moving in this direction, so it will resist the motion of this one and dissipate the energy. Basically it will dissipate the kinetic energy of the mass which is corresponding to this mass. So this will be B y1 dot, because of damping this is the force B and velocity of the correspond proportional to the velocity, and there is a this spring which is also resisting the kinetic, like dissipating, not dissipating, or you can say converting, transforming the kinetic energy to its potential energy. So it will also have a resistive force which is K1 Y1. Now you just have to apply the Newton's law. So MA equal to F net. This is what I have done here. M1 Y1 double dot, which is A, is total force. What is the total force? U minus B Y1 minus K Y1. Sorry, B Y1 dot minus K Y1. Now you got it. The sixth question. Okay, this is the sixth question. So for this circuit, this RLC circuit with a source which is VT. Now this is the input, this VT, and this whole system, it is the input is being provided and we are trying to find the output. So output can be anything, either it can be VCT, I2T or I1, but we are trying to find the dynamics of system, like in terms of I1 and I2. Okay. So what can we write? We know the equations, like dynamics of all the components. For R1, V equal to I1 R1. For L also we know it's V equal to, sorry, V equal to L di by dt. So these things we know, and now we'll apply the laws of KVL, KCL. So we'll apply the KVL. What will it say? That VT equal to this VT equal to R1 I1 T plus L. What will be this one? V equal to L di by dt. No. So L, and what is the current through this L? There is this I1 and I2 both. This is going in this direction, this is in opposite direction. So it will have di1 by dt minus di2t by dt. Yes. What? Okay. For KVL, we say na that we assume a direction of current, and it's like voltage drop along, like along the loop will be zero. So here it is Vt. Now there is a drop across resistance. So because this is going in this direction, this is positive and negative, like this we assuming. And then this is L. Since the current is going in this direction, so there will be this one will cause the drop across this, that will be say. But for this I2 is going in this direction. So this will not cause a drop, this will add the voltage. Okay. So now from there we can find what will be the equation. We just remove the parenthesis and you'll get this answer. This one. Any other doubt in this question? Okay, then we'll move to next question. Now we have to write equation for node 1 applying Kirchhoff's current law. Current law, okay. So all the variables are given and parameters of the circuit are also given. This V is the variable, which is voltage across the resistance. So what is the, we know that equation of for each element, no? V equal to L di by dt, and this one I R equal to V. So if we apply Kirchhoff's current law for this one, no? So I should be equal to IL plus IR. Suppose there is a current going IR and IL. Now for IL, what we can write? Because VL equal to L di by dt. Now this VL is given because this branch and this branch are in parallel. So this VL is equal to V. From there we can write IL equal to 1 by L V dt and IR equal to V by R. This is the equation that will get, and this one is the equation. These are easy questions. So basically you have to apply like modeling of the system. So what are the steps that we have to follow? And then from there, sir has already explained that once we have identified, okay, these are the equations for the elements, then we can apply the laws and find the equation. Okay, any doubt in this? Okay, fine. We'll proceed to next question. So we have come to predator-prey model, where X is the number of prey and Y is the number of predator. And we have to find the equilibrium point. So what is equilibrium point? Where if system is in that state, so it will remain in that state. The change in the dynamics will be zero. For that, finding the equilibrium point for X and Y, no? So dx by dt should be 0 and dy by dt should also be 0. Then we'll get 5x minus 2x square minus 4xy equal to 0. Y minus 3y square plus xy equal to 0. Now from here we can get a trivial solution that if we take the value of x equal to 0, y equal to 0, obviously this will be 0, this will be 0. So one solution is 0, 0. And another we'll have to solve. So it will, like, you can solve it obviously, and that will be this one, 11 by 10 and 7 by 10. Now the thing is that there are two equilibrium points that we have found, and as explained, if we see, this is X, which is prey, and this is a predator. So suppose this is the equilibrium point, and this one, obviously this is the equilibrium point. Now suppose the predator count is decreasing. Okay, so there is decay in predator count. So as predator count decays, what happens? Because of this dynamics of, sorry, prey count decays. So because of this dynamics of predator, what happens? This will increase. So you can say whatever value you take near this equilibrium point, near 0, 0, if you say that this one is increasing, it's like this, means fine. This cannot be go to 0, no? It like negative, because this will always be greater than 0, greater than equal to 0. Count cannot go to negative. So whatever the, however the dynamics we see for one, how the others dynamic evolve, we are saying that it will not reach this equilibrium point. So this is a type of saddle point. This equilibrium point is a saddle point and unstable, because if some state of predator prey like count is nearby this one, then it will not converge to 0. Now if we see this point, this 11 by 10 and 7 by 10, so it is simply like what sir explained, that as prey count decreases, this will increase, and since this predator count is increasing, then this will revolve like this. So this prey count will increase like this. So this will be a kind of, you can say, limit cycle. Any doubt in this question? Okay, fine. We'll go solve the next question. Now says the predator prey model has same dynamics, and it is asking what will happen if number of preys are 0. So simply This is the number of prey. This is 0. This is 0. Obviously, this is 0. This will remain at 0. And what happened to the predator? Now, this one is 0. This is the dynamics of predator, which is dy by dt equal to y minus 3y square. From here, obviously, you will see that this will increase and this will settle to some point. So let us try to solve, because prey's count is 0, so this will increase. What can we write for this? Some constant c. Now, as t tends to infinity, like with time, what will happen to the count of predators? So, what will this tends to? This will tend to 0. So, y equal to 1 by 3. So, y was 0. There's some value. It will go decreasing and then it will go to 1 by 3. Sorry, earlier I said that it will increase. Obviously, if preys are 0, then it will decrease. So this is a answer that it reaches to a constant asymptotically. Asymptotically means with time tends to infinity, what value it reaches. It will not take that value, but it will be approximately to that value. Any doubt in this question? Sorry, in the solution that I provided. Yes. Okay. Yes, yes. This is being recorded, so it will be shared. Okay, fine. Though, okay, fine. So if you all have any doubt, then you can ask. We'll discuss about that related to the lectures that you have gone through. no doubts. That means you all are understanding all the things. This is good. The example that which one? Motor through gear, and then there was a shaft. Okay. Where can I get the question? Lecture 4, no? Hmm. Is it there in website? So is there any PDF or something? This one. Okay, this is lecture. There is no slide and all. And you just see the question where it is. So there is a motor. It is connected to a gearing through shaft J1. Motor torque Tm. We have to find the diameter. Okay, for gearings, we know now that theta1 by theta2 or r1 by r2. So r2 by r1 equal to n1 by n2. Similarly, like transformer. Like, so we this is one thing, and the function of this gearings is to transfer the power. So whatever power is input, that will be the output. So T1 omega 1 will be equal to T2 omega 2. These are two things, equations that we have. Now for this one, if we write the dynamics, that will be J1 theta 1 double dot equal to Tm minus D1 theta dot minus T1. So this is one equation that we are having. Now for this part, load part, we'll write equation. So J2 theta 2 double dot. This will be T2 minus D2 theta 2 dot minus TL, because this T2, whatever torque is being provided by this gear, that will be acting such that it will provide the rotational acceleration to the mass or load, and it will overcome these two. So yes, Kuldeep, you have raised hand. Any doubt? Oh, so these are two equations. Now from here, if we see this equation, so that we can write this T1 omega 1 or T1 equal to T2 omega 2 by omega 1. So if we try to see this from the this side, motor side, then this will be J1 theta 1 double dot plus T2 omega 2 by omega 1 equal to Tm. Now for T2, we can supply this one, this equation, and then we'll get some equation. Also, we have seen this omega 2, or we can relate this theta 1 and theta 2 through this one. So basically we are replacing N1 by N2. Is it given, this N1 N2 number of teeths in the gear? Not. Okay, this is given N1 R1 and N2 R2. So if theta 1 by theta 2 is this one, then we can also write the same for omega 1 by omega 2 and theta 1 double dot by, or we can say alpha 1 by alpha 2, which is angular acceleration. And we just have to replace this in this one. Then we'll get all in terms of theta 1 dot double dot if we replace theta 2 double dot by that one. And this we can see that whatever dynamic equation that we'll be getting will be from this source side. And from load side, if we see, then what we have to do, we have to replace this one, this T1 by T2 equation. This is a kind of just writing dynamic equation like for the coupled system. What is the doubt in this? Like apart from writing the dynamics, because this has to be solved, and after simplification, you'll get the equations. Basically, for any mechanical system, no, when you are doing the modeling, you have to see like whatever the force is, no, it is trying to accelerate this one. So it will provide some energy, which because we are talking about dynamics, okay, dynamical system. Whenever we are saying mechanical system, so we talk about kinetic energy. So this J theta one double dot. Now some energy will be given to this mass, which will cause the kinetic energy. That is, if we say rotation, then rotational kinetic energy. And the energy from input, some will be like dissipated due to the damping, which is the friction force that will be dissipated. And some, if there is a load, then it will try to overcome that load resistance also. So from that we are getting these equations. Similarly for this one, because here the driving force is Tm, the torque from motor, and from this side if we see, the driving force is T2, which is coming from this gear ratio like thing. Hmm. N1 and N2 is the number of teeth. So when you say gear, so it's not like circular, it's having teeth. Uh, I think you have seen a cycle chain. So there is a chain like this, and it has some, that's how it moves like. Or even if you car, if you see transmission, then its physical structure is like this. So it's like this, and there will be a small gear. So a small gear means, a small size gear means that this its radius is small, its speed will be high, because these two have to rotate by same angle at the time. This is the physical structure, but if we see from the what is the significance of it, what it is doing in actual dynamic, then it is just transferring the power. So whatever the input power is, that is being transferred. This is idealized case, but obviously there will be some friction loss here. There is here also, but its dynamics we are neglecting. Okay, and oh, any other question or anything from lectures that you are having, you are confused with? Have any confusion or related to lecture? Okay, so what is your doubt? 7, 8, and 9. But like if you can tell me the question, then I can tell you. Like I can give you a hint, but I cannot tell you the answer. Anyone having any doubt? You have enrolled in this course, no? So you should try to utilize this time. Then if you ask question, then next time I'll also have to prepare, like work hard on that. Hmm. So this is somewhat related to this question, no? This one. That there is a pendulum given and its time period is half of initial period. So what should be the length? So you know the procedure that we are first linearizing this and then we are finding the time period. Like obviously you got the time period equation, so you can directly put it in equation and try to find out what should be the length. Yeah, please ask doubts. Otherwise, I will ask questions. Sorry, like, just trying to motivate you to ask doubts. So, what do you think? For linearity, what should be the condition that has to be satisfied? That if you give alpha x1t plus beta x2t, then is the output alpha y1t, y2t? This condition you check, you apply x1t, x2t, you'll find y1t, y2t, and then see whether it is equal to like the summation of, or you can say weighted sum of these two is equal to y of alpha x1t plus beta x2t or not. Just simply write equation, you're able to find. And one more thing about the linear system is that if the input is 0, then output will also be 0. Because like this is linear, no? So it's like not able to write. So if you see this system, if you provide input equal to 0, then output is a some constant. But here, if you see this one, then if this is 0, this one is also 0. So should I revise the concepts? Okay, if you have gone through lectures, so in the first lecture you have gone through, because you are obviously joined a control engineering course, so you will talk about systems. I mean, the fundamental idea of control system engineering is that if there is a system or some which can be representation of any physical process or biological process, anything, even economics, if you see, there can be some system we can define there. And then we are seeing that, okay, this is the output that we are seeing. Like, if we consider this stock market thing, but obviously uh, there will be this prices in a stock market that we see, and there are various factors that is influencing this. So it's maybe what is the economy of this country or another, all those things, and it is going through some process, then it is giving this output that we say is like say that okay, so we are getting news that Adani has lost this many billions of share and all. So these play an important factor in our daily lives also. But for economics is what we say that this system we don't know. So some system we may be knowing, some system structure we don't know. So considering that we know the system, so we'll start with this one in control engineering, and we know what is the input to it, what is the output. Now if we know input and output means response of the system, then we know that okay, this is performing well or not. So suppose the example that sir has given, there is a room temperature control system. So there is a heater in the room, and it has to maintain a temperature. Or so if we just power supply this, we'll see what is the temperature of the room, and this is being disturbed by how many persons are entering and leaving the room. So this is disturbance. Now this system behavior will change according to that, and the purpose, like our aim is that, or we can say controller aim is that it tries to get desired response from the system. So suppose it is cold outside and the temperature has to be maintained at 25 degrees Celsius. So the heater has to be maintained at that. Now what controller does, like this is the thing that it will just give the input to the, it will just switch on, like suppose we switch on and then we'll see that okay, this is the temperature of the room. Now what we say that suppose there is some uncertainty comes in, like there is disturbance, so this temperature will change. But what we have calibrated earlier, that if we supply, suppose we can vary the voltage with 0 to 100 volt, and we have calibrated okay, we'll supply 50 volt and it will give this much temperature, it will keep the room temperature at this much. So this disturbance rejection is an important part. Now if we take feedback of the response, then we can have a system, like a component in this closed loop system, which will try to maintain the temperature at that point. So where there the controller is needed. So for understanding the whole thing, first we need to understand the system. Now for controlling the system, we have to understand system, what type of system it is. Generally we deal with linear time invariant system. So these are the examples that you had in lecture, and these are the things that we have solved examples regarding this only, that different type of system we see. And we don't deal with a static system because it's a static, so we don't have to control anything. No, it's dynamics, then only we can control, we can change that okay, it should not go out of limit. Suppose there is this actuator which has a limit of rotation. So suppose there is a valve in a chemical plant, so there may be an constraint that okay, it should not open more than 30 degree and all. So all those things has to be considered while controlling the response of the plant. Okay, so you have gone through the classification of system. Obviously there were some examples for all this. And then we have also seen what is the causal non-causal system, that if the output depends on present and past time instance, like then this is a causal system. Otherwise, if it depends on future input as well, then It is a non-causal system. Then after reviewing that, we came to controller, that what is the function of controller? It's basically try to achieve the response of desired response of the plant or system that has to be controlled. And we talked about disturbance. Okay, so one of the function of controller should also be that it should reject the disturbance. So there came the concept of feedback, that if we have feedback, then it is possible to control the system as well as reject the disturbances. Because if we do the open loop control of the system, then because of disturbance, the output that is be desired, that may not be achieved. Like in temperature control system, so if person are coming and going, the door is opening, then uh, if we have this type of a structure, then the temperature may vary. Whatever the desired temperature, that will not be achieved. In that case, the feedback comes in play. And in control engineering course, we'll be dealing with the feedback control system. Okay, so we came to know what are the different components in this feedback control system, like plant, so system that has to be controlled, and then we had this control system controller, which is controlling the which is giving the input to the system, or we can say which is giving the input to the actuator. Because generally what happens, the controller that we have in the control system is a embedded system kind of thing, or it's uh, low voltage system. So it will give digital output or some 5 volt within like low voltage output. And the plant is like chemical plant, and there's lot of, or we can say microgrid and all, like then there are a lot of energy that is required to be given into the system. There it is not possible to realize that input using that controller. So there comes the actuator, which realizes the input given by the controller. And we have seen the various signals like output, disturbance, feedback, all those for different types. So these are the things that was discussed in the first lecture. And then once the overview was given, that okay, this is the overview of what is the control system, then uh, it was started with modeling of the system. So in lecture 2, there were different steps of modeling, like what has to be considered when modeling the system. And one more thing, that whatever system we are trying to control, that is a physical process or something, we are just modeling that with mathematical. It's not the actual system. This is an approximate of the actual system. So whatever controller will be designing in the course, that will, maybe it may happen, and that will act like perform good for the mathematical equation, but may not perform well for that much well, like accurate for the actual plant. So these things also have to be kept in mind, and that's why system modeling is also an important domain, or we can say system identification, where we try to find out the dynamics of the system. And there are different ways that sir has also discussed, that one way is to just use the different laws that we have studied, like Newton's law, Kirchhoff's current law, all those things that we have studied. Another way is to get the data, do the experiment, supply some input. Now, while supplying some input, we need to make sure that we are supplying sufficient input that will be able to characterize the system dynamics. Okay, and we'll get output from the input output data. We are trying to get the dynamics or mathematical model of the system. So this is also a domain of research. So this is a mathematical model thing, and then in this course we'll be dealing with these 3 types of mathematical model. Generally for dynamical system, these are the uh, different ways of representing the models. So for time domain, we have differential equation model. And since we will be dealing with just one independent variable. So we say ODE, like ordinary differential equation. But there are various systems which can be represented with partial differential equation also, like traffic. If we see, so traffic, we see the traffic dynamics will vary with time also and with distance also or space also. So there are two independent variable and this is varying with time and space. So that can be represented with PD. In this course, we'll be dealing with OD, and then there is this transfer function model. Since we are considering linear time invariant system, so we'll deal with transfer function model. So their assumption. So this is to simplify our analysis, and this analysis is used in uh, for nonlinear models also, and for while solving, like if we have complex models with PDs or nonlinear ODs, then we can try to simplify things and bring it in linear domain and then time invariant domain, so that we can use this approach of modeling to design controller or to analyze the system. And then we have a state space model, that is also a time domain model, but here the dynamics is represented by states. So these are the different models, and this is one example. And this we talked about analytical modeling and experimental model. These are various steps that has been discussed. And then in the third lecture, different elements and what is the dynamics of different elements have been discussed for electrical system and mechanical system, like resistor, inductor, and if we say then capacitor. For mechanical system, this damper or mass and uh, spring, how these elements behave, that has been uh, discussed. And then after finding what is the uh, dynamics of individual elements or the elements of these type of domain, or we can say electrical circuits or we can say mechanical thing, then we try to do like some examples we solve where these equations based on these element dynamics, overall system dynamics was obtained. So one is this quiz control. This also we discussed in example, and transformer. Like if we are trying to find what is the efficiency of transformer for different loads. So what we say, since the purpose is to find efficiency, so we'll try to model it such that we can uh, it the model shows the losses and all in the transformer, and this is how it is modeled and all. So all those things have been discussed. Then this one is on Lotka-Volterra equations, predator prey model, couple dynamics and all. So this has also been discussed. Okay, I think you all have understood everything. If any doubt, you can ask. I'm just trying to revise. This is very concise, whatever I have told, but yeah, if you ask out, then I can elaborate more. Yes. Okay. Fine. This is the example which talk about time invariance or time variance. This is the dynamics of the system. Now we have to see whether it's time invariant or not. So for time invariance, what we say that if there is an input xt to the system and we are getting output yt, then to the same system, if we apply input after some time, suppose x of t minus tau. So this is how delayed version of input is represented. Then output will be same, but since we are applying after some time tau, which is the time difference between applications, so this will also have this type of equation, mathematical representation. So this is the input and this is the output. And then if after time tau we are applying, this is the input and same is the output pattern is same, like same output but time shifted. So this has been shifted to, this is the shifting. Earlier it was like this. This is a time invariance thing. So if we consider like generally the circuit which has constant parameters like RLC circuit and all those, we have this RCL, or if we have a mass spring damper system, these values are constant, these parameters are constant. So generally in this kind of system, since these values are constant and this is a linear system, so this one, if we provide the input, whatever input we are providing, suppose this is a RL circuit, providing voltage. We are trying to find the response. We gave the input and we are saying this is the response. Now after 2 days, 3 days, whatever time delay you give and you again provide same input, then you will find same type of output. This is a delayed version. This is a concept of time invariance. So if we write it mathematically, it says that if we apply xt minus tau, the output should be yt minus tau. But for this example, if we see yt minus tau, this is t minus tau x of 2 t minus tau plus 2. This is 1. And if we apply xt minus tau, what is the output? T x of 2 t minus tau plus 2. Now we can see this y t tau that we have obtained after some time duration tau. If the input is applied, then this is output, but the shifted version of output is this, which is not equal to this. So this is not a time invariant system. So have you all submitted the assignment for first week? Any more doubts that anyone want to ask? Okay, so the recording will be uploaded. You can see the recording, whoever has missed and all. Or if you still have any doubt, you can go through the recording and see that. Or you can also ask me in next session. PDFs also I'll share. I don't know it will be shared with you or not, but the recording will be available. Okay, fine. Then I think you all have enjoyed this session. Then you all can leave. We'll end this session today. We'll meet next Sunday for interaction on the second week for content. And if you have any doubt, meanwhile, you can keep it with you and you can ask me next session, even if it is related to this session. Okay, thank you. Thank you all.